Okay, so let's continue from where we left off last time. So we were studying local properties of analytic homomorphic mappings. Okay, so what we did is that we take some point z naught in C, or actually, yeah, let me take z naught in some open neighborhood, maybe omega in C, and then we have f from an analytic function on omega. Okay, so this is homomorphic. And then we wondered about its behavior. Okay, and where we left off was, well, let me summarize a little bit what we were doing. So we were trying to understand the behavior of this function locally around z naught, so in a very small neighborhood. I mean, much smaller than just this open set omega where the function is defined. So from last time, so we saw that there are sort of two possibilities. So the first possibility is that so f prime of z0 is not 0, and here we have a very particular thing for analytic functions, actually, which is that this is equivalent to being locally one-to-one. Okay, so this is of course absolutely not true in real variables, right? So, but this means locally one-to-one, and you have an inverse. Okay. But of course, this does not. Okay, I will address this, but it does not imply this globally one-to-one. For example, you can consider z goes to v to the power z, which is, okay, its derivative at any point is non-zero, because the derivative is just e to the z, which is not 0, but of course this is periodic, so it's not.
It's not the same thing in real life.
Sorry?
The function from R2 to R2, where the Jacobian is inversible at point, then it's locally diffeomorphism, right? It's the same.
Oh yes, no, you're right. You're right. Yeah, I was confused. Okay, yeah, but it does not imply the globally one-to-one. Okay, so that's good. So we had this, and your function will be locally invertible. Okay, so there exists local inverse. Okay, in a neighborhood of this point that I last time used to call W0, which was the image of Z0 under F. Okay, so there exists a local inverse in this neighborhood, going back to omega. And the other possibility was that F prime of Z0, okay, this 0, of course. And then we had this peculiar behavior with n-fold coverings, right? So remember, so for example, z goes to zn, something like this. If we take this to be f, then we said that, so then have an n-fold covering. So then a neighborhood, so the image of the neighborhood of Z0 covers a neighborhood of W0 n times. Okay, so this map is 1 to n. We want to say. Okay. So if you take the image of the unit disk under this map, you get something that winds around the unit disk. The image is the unit disk as a set, but it winds around n times. So it becomes n times the unit disk. Okay, so you have these behaviors. And as a consequence, we also have this theorem, which is useful. So we have the open mapping theorem, which said that if f is analytic, if it's holomorphic, and non-constant, then F is an open mapping. Okay, and this meant that, so if A inside omega is open, then also the image under F is open. Okay, so it sends open sets to open set. Okay, so you remember we had this, and all this was due to this proposition that we saw last time, the confusing proposition, if you remember, or the one that was just a little bit hard to digest, let's call it that, which was simply that if you have n zeros in the image, so if you have n solutions to f of z minus w0, so this has n solutions in a small neighborhood of, I mean, if this has n pre-images in the, so n solutions to the, if I put equality here, okay, or n solutions of this in a neighborhood of, yes, if I have n pre-images of this, then I also have n pre-images of f of z minus a for every a in a small neighborhood of w0. Okay. So this is n roots. Okay. This also has n roots for every a in a small neighborhood of w0. Okay, so what we said was basically that, I mean, what we said was basically the following. So I didn't mean to write this seriously, it was just a remark, so what I want to write is, so recall that we looked at this number, the number of zeros in W0, which was this 1 over 2 pi I, the integral over some small curve, and then our f of z over f of z minus W0 dz. So you know that this is the number of zeros, okay, of an analytic function, so equals number of zeros. Yeah, that's right. Thank you. So number of zeros of f of z minus w0 inside this gamma. So let's say that this is actually the z minus z0 is equal to epsilon. So let's say it's a small disk. I choose that just so we know that it winds around once. Okay. Could have taken any gamma with winding number 1. So that inside this small disk, that's an epsilon. And then we said that the function a maps to z of a, which is now the number of zeros of a different function, f of z minus a. So this function is continuous, but it's not continuous, okay, maybe everywhere, because at some point it will change, but it is continuous in a small neighborhood of omega 0. So let's say that it's in w minus w0 less than delta. Let's say it's continuous in here. And then, because z of a takes integer values, okay, even natural numbers, okay. In this case, this implies that it is constant in this small disk. So it means that if we have n zeros to this equation inside this small disk, z minus z0 equals epsilon, then we also have it for any other a, I mean for when we replace this equation by f of z minus a for any other a close enough to w0. Okay? Yeah, I guess, yeah, maybe I should write a here instead of w. Okay. So this was the idea of this proof. And this implied the open mapping theorem, okay? Because it means that this set here, now let me write it in this way, is inside f of this, should I call it omega? No. Yeah, f of omega. No, f of, no, it's a small neighborhood. So f of this set. Let me write it. Okay, so this set, for W, set that this was, excuse me, writing this. Okay. This set is inside this set. So in particular, such a small neighborhood of W0 is still inside f of omega. Okay, or f of A. So A open implies that this disk around W0 of radius delta is inside f of A for some delta. Okay? In otherwise put, f of A is open. Okay, so this of course is some delta. Okay? So this is what we said last time. No? You look a little bit confused. I have to admit. Very worrying. Okay, any questions? Are you sure? Okay. So let me remind you of something that I know that I think you did follow last time. So my open mapping theorem. Okay, so if this f prime of z0 is not 0, I mean then f inverse exists, and so it's in this situation. So f inverse exists, this local inverse, and this is an open mapping. Sorry, f inverse sends, yeah, it's an open mapping. Yeah, open mapping, exactly. And that means that f inverse is continuous. Okay? Yeah, because f inverse takes open sets to open sets.
It is f.
F open mapping, exactly, which means that f inverse is continuous. Yeah. Well, okay. So means that no, hang on. So okay, f inverse continue. Yeah, great. Okay, but then you recall from an earlier lecture. But from an earlier lecture, we then know that this implies that by this continuity, this implies that f inverse is in fact differentiable, and you even have this this formula that f inverse of W, f inverse prime, okay. F inverse prime is equal to 1 over f prime of f inverse of W, this usual formula, right? Have something like that, so it's differentiable. In other words, f inverse is also analytic, because it's differentiable once, it's going to be, it's complex differentiable once, it's going to be complex differentiable infinitely many times by everything that we have seen. So, what is the corollary? So, the corollary that we have proven is that if f prime of z0 is not 0, then f maps a neighborhood of z0 conformally and topologically, but let me first erase this so I can write here. Okay, conformally because it's a holomorphic mapping, but it also maps topologically. So what does it mean that you map topologically? This is not really a usual terminology maybe, but what I mean is that it's continuous with a continuous inverse. So I mean that it's a homeomorphically, or it's a homeomorphism. Okay. So homeomorphically onto a neighborhood of this W0, which is onto f of Z0. Okay? So it cannot do, whatever it wants, but it maps a neighborhood very nicely onto a neighborhood of f of Z0, which is not to be taken for granted. I mean, of course, this is related to the first situation I had, right? If f prime of z is non-zero. So question, what if f prime of z0 is equal to 0? Now, in general, so previously I've just talked about this map z to the power n. But what happens in general? So if f prime of z0 is not 0, basically everything is super nice. Right? It's even homeomorphic. Actually, it's even biholomorphic. So I should maybe write that. I can write that. Wonder where you put my color control. Okay, so it's even biholomorphically. I don't know if anybody knows this word yet, but I will mention it probably in a short while. Anyway, again. But biholomorphic means that you have a holomorphic map whose inverse, which is bijective, and whose inverse is also holomorphic. Okay, so what about the general case? So in the general case, let's assume that of z minus w0 has a 0 of order n at z0. Then we can do our usual thing. So f of z minus w0 is equal to z minus z0 to the n times g of z, where g is analytic, and g of z0 is not 0. So since it's not 0 at this point, it means that in a small enough neighborhood it's not 0. Okay? So there is a small enough neighborhood such that g of z0 is not 0. So this means that we can find a holomorphic branch in this small neighborhood, in a small enough neighborhood, of the nth square root of g of z. So, well, let me just say that this implies that j of z is non-zero in a small neighborhood u of z0, okay? And then this implies that can find a holomorphic and single valued branch of a logarithm. First of all, this was your exercise, okay? Of log of g of z, okay, on this neighborhood u. So you agree with this? Exercise 7 on homework 3 or something like that. So you can find this. That's also a holomorphic and analytic, well, a holomorphic and single valued branch of square root of this, so of g of z to the power 1 over n, which is defined as e to the 1 over n log g of z using this branch. Okay, so you can define the nth square root. Okay, and call this function now h of z, just for notation. So this nth square root, we call it h of z, this branch. So this implies that on U, we can write, so on a small enough neighborhood of z0, we can write f of z minus w0. Well, actually, so let's put w0 on the other side, so it's equal to w0 plus z minus z0 h of z to the power n.
Is it exactly on you or on something inside you?
Yeah, on a small enough neighborhood. On a small enough neighborhood. But in this case, let's see. So if log is defined on this small enough neighborhood, yeah. No, but I mean, anyway. So in all this business with the local things, so you don't really want to ever write out exactly where it is defined, to be honest, because the philosophy is simply in a small enough neighborhood, and we don't care, you know, if it's of whatever this neighborhood is. So we just want to know about locally on a small enough neighborhood. So yeah, locally, then you write like this. So f of z can be written like this. And then we can consider what this function here does. Okay. So well, let's just see. So f of z is a composition of these three things. So a translation, z goes to z plus w0, so just the translation. And z goes to zn, okay, which gives an n-fold covering of this. Okay, and finally of this z minus, z goes to z minus z0, h of z, where h of z is analytic. And here we want to understand what this does. So here we note that, so we look at the derivative. So we want to know if it's well behaved or not. And to see if it's well behaved, we do the following. Look at the derivative. So where d dz of this. Okay, so it's equal to h of z plus z minus z0 h prime of z. And okay, so this h prime of, yeah, so this is equal to h prime of z0, actually. If I take this derivative in z0. Yeah. Sorry, so it's equal to h of z0. Yeah, so this in z equals to z0. This is equal to h of z0. And h of z0 is not 0. So all of this works. So this is not 0, so this means that maps this neighborhood, maps a small neighborhood conformally and topologically onto its image. Okay. So it's composition of three things, where the first one is obviously very nice. I mean, it just translates whatever you have in the plane. And you have this third part here just maps conformally and topologically. So it doesn't do anything bad. And then you have this n-fold covering map. So what we have shown is essentially that any holomorphic map can be viewed sort of as the composition of these things in this case. So this Zn is a very important prototypical example to understand. And let me write down just the conclusion. So the conclusion is that the image of the neighborhood of Z0 covers a neighborhood of W0 exactly n times. Okay, so this is always true. If you so the assumption was you have a 0 for order n at Z0. So if you have a 0 for order n at Z0, then the image of the neighborhood covers the neighborhood exactly n times. Okay. Yeah, and then also I had written down here a small remark. As usual, it's always nice to contrast with a real case. So note. So this is of course, so so note, this implies that if f prime of Z0 is equal to 0, then you have an n-fold covering of the image of the small neighborhood around Z0. So it means that you cannot define, there is no local inverse, right? So which implies that then f does not have a local inverse around Z0. Okay, so this is an important conclusion to understand, and this is in contrast to the real variable situation, where we can consider, for example, such a function, x goes to x cubed. Okay, so at x equals 0. So here, of course, so this is f. So then, of course, f prime of 0 equals 0. But it has an inverse. This inverse, which is continuous. Okay, but not differential. Okay, but so anyway, I mean, in this example, you have an inverse, actually, a local inverse, even though f prime of 0 is 0 to this point. But in the complex variable case, this cannot happen. Because of this reason that if f prime of z0 is 0, then any small neighborhood is mapped to, I mean, covers n times its image. So you cannot get away from this. You cannot get a bijective map, define the inverse, if f prime of z0 is 0. Okay, so now I took you on this long and, by the look of it, confusing trip to tell you this. Any questions? If not, I'm sure you'll be happy to hear, but I'll move on to the maximum principle, which is a very important result. So actually this maximum principle you can use to prove this thing outside of a video here. Okay. So this gives maximum principle. Okay, so maximum principle is a consequence of the open mapping theorem. And the maximum principle, so this is something that is actually extremely important in mathematics, especially if you want to do any kind of geometry or analysis. Then maximum principle is very important. Or PD, by the way. And because this holds for many classes of functions, it holds for holomorphic functions and it holds for harmonic functions. And as you've seen, we proved in, I think, in our first homework that the real and complex part of holomorphic functions are harmonic, but actually also every harmonic is function is locally the real imaginary part, the real part of a holomorphic function. So they are very closely linked, and the maximum principle is extremely useful. It says the following. So if f u to c is analytic on the domain u, so if, and here comes the statement. So now if the absolute value of c attains a maximum on u, so u here is open, okay? This is very important. So this here is open. This is very important. So in this word domain includes that it is open. So if it admits a maximum on u, then what is the conclusion? The conclusion is that u is, sorry, not u, but f is constant. Okay. So this is very interesting. So why is this? So maybe I should write down an alternative formulation also. So alternatively, you can say that on every compact K inside of this U, F admits, so F is continuous, it admits a maximum on a compact, right? But the maximum has to be admitted on the boundary. Admits its maximum on the boundary of K. Okay, so let's say you have an analytic function on the unit disk. Sorry, absolute value of F. Of course, I cannot talk about, why am I talking about absolute value of F and not F?
C is not ordered.
Good, first thing I said in the course. Closing the circle, C is not ordered. So I have to talk about the maximum of absolute value of F, because C is not ordered field. And so, I mean, this is how I like to think about it, actually. That it attains its maximum on the boundary. But if you have an open set, the boundary is not inside the set, so if you had a maximum in the open set, then it would have to be constant. And the proof of this is very nice. The proof of this is very easy. Maybe you already see it. So you use the open mapping
I think that you
theorem.
should said a bounded domain, no?
Yes, I mean, yeah, so this is sort of implicit, I think, in this this domain. Yeah, this.
No, it's
in
correct
this
that it said, but the second
Yeah.
one, to talk about the boundary, if it's not bounded, then boundary can go to infinity, so...
Yeah, then
so
it makes.
I mean that if u is not bounded,
Mhm.
the boundary can be a u, that's what I mean.
Yeah,
Can
but still.
intersects u.
Yeah, so if u is not bounded, then you have a maximum in z equals 2.
Yeah. No,
Then it still cannot happen, right?
I mean,
Yeah.
when u is not bounded,
Mhm.
it's not instead it's not bounded. It's the boundary of u. The
Mhm.
intersection of the boundary with u is always empty.
No, yeah, but look, so if you have, let's say u is the whole complex plane,
Yeah.
something like that.
For example.
Let's just think about it. Yeah, what happens? And then let's say that this one has a maximum.
Yeah. So it's constant, yeah, so you will.
Yeah, it has a maximum somewhere.
Yeah.
Then it still has to be constant. I will show you the proof now, and you'll see the same proof will apply. So.
If it's not C, in C it's okay, but when U is not bounded, but still not the whole.
But not your complete? Well, then it's still fine, because I mean, so U can be whatever you want. It goes to infinity,
Yeah.
but you assume it has a maximum somewhere.
Yeah.
And this maximum is inside some bounded disk, right?
Yeah.
And then you show it's constant,
Okay, so
and then you show it's constant on this disk, and then by the identity theorem it has to be constant everywhere, because if it coincides with a constant function on some disk,
Yeah.
which in particular has accumulation points, then it has to be all over together. So this works even if U is not bound. Okay, but think about it like this. I mean, if you want, I prefer thinking about it like this. Anyway. This is the nice one. So the proof of this theorem is very nice. So assume that it has a solution or not. I don't know if you want to do it, think of it by contradiction or not. But anyway, the idea is this. So, okay, let's put W. Let's consider any f of z0, any point in the image here. And I could write down, assume it's a maximum, and then write in 1 minute it's a contradiction, or just say that it's any point, and then show that in the neighborhood of this point there must be a larger value, okay? The absolute value. So if you take any point, if you want, you can think of it as a supposed maximum, which cannot exist. Okay, so here is wz0, and here is 0. By the open mapping theorem, you can find a disk here, a small disk, and this whole disk here, disk of W0 delta, is inside f of A. F of A was by a set called A, f of U, okay? Inside f of U, for some delta small enough. This is the open mapping theorem. Okay? So this set is still inside f of U. It means that every point inside here is of the form f of z for some z in U. It's in the image. And if I look here, so here is 0, this is very important. So obviously, inside this disk, I can find some point which is further away from 0 in absolute, the absolute value is larger than the absolute value of W0. Okay, so in this disk, there exists some W such that the absolute value of W is strictly greater than the absolute value of W0. Okay? But by the open mapping theorem, this is inside f of U. So every point is the image of some point in U. So this means that there exists a Z in U such that absolute value of f of z is greater than absolute value of f of z0, which was the definition of W0. So you see, wherever, if I say I have some value of my point here, I can, I can find a small enough disk where all the points are in the image of U, then this must always hold. So in any small disk, I can always find a larger value, large point with larger absolute value. So it cannot have a maximum. Okay. So there is no maximum attained by any point in U. And this proves the theorem. Okay. On the other hand, if I was on a compact, then this does not show that it's impossible. I mean, it just shows that the maximum cannot be attained in the interior of the compact. And since we know that any continuous function admits a maximum on a compact, it has to be on whatever is not the interior, so it has to be on the boundary. Okay? So this is the proof of the theorem. which is very nice, I think. In any disk with a point further away from 0 than the center of the disk. This is the proof. Okay, and now, what do we do? Okay, first thing we do is we say that there is no maximum principle in real analysis. This is the first thing. While I erase, can someone think of an example of some real single variable function that does not satisfy the maximum principle?
Single variable.
Yeah, just to not make it too complicated. I don't want you to give me a
X squared at 0.
x squared at 0.
A minimum, not maximum.
Yeah.
1 minus x squared.
1
1 minus x squared. Okay, very good. So remark. Okay, so f of x equals 1 minus x squared for x now in real numbers does not satisfy the maximum principle. Okay, because we have 1 here, and you have this thing, and it does have a maximum in an interior point of open set. But the thing is that this cannot happen in complex analysis, okay? You cannot have a local maximum. So if this was complex analysis, then there would have to be some direction where actually the absolute value goes up. So this is the miracle of complex analysis. Okay, but having said that, we now proceed to a very nice topic and a very nice theorem. So now we go to analytic maps on the disk. Okay? So the disk, you can interpret unit disk, but really topologically, even biholomorphically, there is no difference between the unit disk and the disk of any other radius, so on the disk, right? So we will consider the unit disk. So now we have the following very important result. Schwarz-Lemma. Okay. Who has seen Schwarz-Lemma before?
Schwarz or Schwarz?
Schwarz, Schwarz.
Without T.
No, this is without. I mean, this is confusing. So I did my PhD in the laboratoire Laurent Schwarz. So I should really know, but still I am confused. Yeah. So Schwarz. So no, this is Schwarz like this, and this is this Laurent Schwarz?
No. Laurent Schwarz is with T.
No.
Oh.
Is it? No. I'm pretty sure, I mean, my PhD is from there, I should really know, but I don't, it's very embarrassing. But okay. Yeah, I forgot. Laurent Schwarz is a French mathematician who won the Fields Medal. Okay. If this is this guy, I am afraid to say. But anyway, this is a very useful lemma, okay? So this maximum principle, extremely important, never forget it. This Schwarz lemma will be extremely useful, always. Advice. For sure you will use it at some point in any exercise or exam from now on. So it's extremely useful. So it says that, so it's about analytic maps on the unit disk, this Schwarz lemma. But you can also translate the result into analytic maps on other domains by first mapping the domain onto the unit disk and then mapping it out. But okay, I'll come to this later. So let's.
Which one is with T?
Is this one with T?
No. Yeah, no, the French one, Laurent Schwarz. The French one is with T. This is not the French one. This is not
Really?
implementation. Yeah.
Is it?
Yeah.
Oh my god.
It's not the same.
Are you sure?
Yeah. I
Oh.
asked.
I see you just fixed it. Yeah, okay. Thank you. So this is someone else. So it says the following. So F analytic, so it says this. So let's say that F is a map from a unit disk to a unit disk, which is analytic. And we assume that f of 0 is equal to 0. Okay? So we have these two assumptions. And these assumptions are not extremely restricted. Okay? So let's say that I had a map that was from the upper half plane, let's say, to the upper half plane. Then you know that I can map the upper half plane to the unit disk by a Möbius transformation. Okay, so let's say, let me just use this as a kind of scrap paper. So let's just say that I had f from h to h. Then I can map h to d via this Möbius transformation, which is maybe something like this. Okay? And then I can map it, and then I can map it, and I have also an inverse, like this. So then I can consider this map, h to h, as a map from d to d by first taking a point in d, sending it to h, then taking f, and then sending it back. Okay, so let's call this d. No, this is f. Sorry. And this is, yeah, so here I have this. Okay, and here I have the inverse of that map. And then I can still obtain such results. And if f of 0 is not 0, then I can again compose with a Möbius transformation such that it is the case. Okay, so if f of 0 is a, which is not 0, okay, you can take a Möbius transformation that takes the disk to itself, but takes a to 0. Okay? And then you end up in this equation. Yeah. And I like this trick, so I will for sure ask you about it at some point. So. Okay. So f of 0 is 0. So this is just to say that this is not such a restrictive thing. You know, it's not like if f of 0 is 1/2 that it's such a disaster, you know, if it's 1/2. So this applies to a wide variety of things, and not just a specific math. So then, what is the conclusion? If you have a map from D to D, such that this is satisfied. Then the first thing is that the absolute value is not increasing. Okay? The absolute value of f of z is less than the absolute value of z. Then you have the second thing, that if you look at the derivative in 0, then its absolute value is less than or equal to 1. And 3, if equality holds in 1 or 2, okay, for some z. So this is of course for all z. Okay. So if equality holds in 1 or 2, for some z0 and d, then actually you have almost the identity map. Okay? Then f is almost the identity map. Yeah, almost the identity map. Then f of z is equal to lambda times z, with absolute value of lambda. So lambda is a constant, okay? Well, lambda is a constant, and absolute value of lambda is 1, okay? And this means that it's a rotation, okay, that sends z to e to the I theta times z, because every absolute value, every constant absolute value 1 is of this form, as you know. So this is the famous Schwarz lemma, okay? And this one is extremely useful in many ways. For example, if you want to show that maps are unique in any way. So if I ask you, if you want to solve something like to what extent are conformal mappings unique So if you have two conformal maps that go from some domain into D, that maps maybe the same points to 0 or not even that, then to what extent, what can you say about the relation of these two maps? Okay? So are they maybe unique? Or almost unique in some sense up to a rotation, or maybe it's, they differ only by Möbius transformation, or such things you can typically show with Schweitzer lemma. Okay, so I will for sure put some exercise like this on the homework sheet. And
condition that 0 if in D minus 0. I mean, another point, not because theory is assumed for 0.
Yes, very good. Thank you. Thank you. Very good. Thank you. Yeah. So you can show many things with this. In particular, you can understand the automorphisms. But first, before I get ahead of myself and start talking too much about how great this is, let me prove it. Okay? So the proof is apply maximum principle. The following function, g of z, which we define as f of z over z when z is not 0, and we let it be f prime of 0 if z is 0. Okay, so of course this is now analytic. Okay, f of 0 over z had no removable singularity. This is analytic. And absolute value, so in the disk, absolute value of z less than 1. Removable singularity. Now, let's see. What happens when we apply the maximum principle? So let's do it on this form of taking a compact, maybe. So I take a smaller disk of radius r, but I take a closed disk. This is the typical compact inside the unit disk. And then the maximum has to occur on the boundary. Okay? So take a compact disk. Okay, so the closed disk here, where r is less than 1. Okay, so of course it's greater than 0 and less than 1. So consider this disk. So then the maximum principle occurs somewhere because it's a continuous function on the compact, and it occurs on the boundary absolute value of z equal to r. So this is where the maximum is. So this implies that the absolute value of g of z, so the maximum of the absolute value of g of z, of course. Okay, so it's equal to this, by definition, okay, by the way I constructed g. And it's less than or equal to the maximum on this circle, but on this circle the absolute value is always so this one actually is less than 1. Okay, by hypothesis, right? Because so this is important to note. I wrote this. This means that f of z, in my assumption I have f of z is less than 1. Okay, strictly less than. Okay. So this is for any z such that the absolute value is less than or equal to r. Okay, and then you let r tend to 1. So as r tends to 1, have that absolute value of g of z is less than or equal to 1. Yes. So it's less than or equal to 1. So f of z is less than or equal to absolute value of z. Okay, so this was the first part. Okay. And for the second part, well actually, and this also follows. Okay, so we get these two parts. So just from seeing this and looking at this definition, we get both these parts, right? 1 and 2.
Excuse me.
Yes.
Why this is less than 1 over r?
What do you want it to be?
I don't know, but I don't know why is it less than 1 over r.
Okay, so this is by the maximum principle.
Okay.
So because so this is the maximum principle. Because on the boundary it is equal to 1 over r. So it has to be smaller on the inside. Very good. So now, so you agree that 1 and 2 follows now by g of z and the way I define it. Yes? And then finally, so now we have to see what happens if equality occurs. So if equality occurs, then what does this mean? So equality occurs in 1 or 2. It means that absolute value of f of z is equal to absolute value of z, or absolute value of f prime of 0 is equal to 1. It means that the absolute value of g of z is equal to 1 somewhere, right? Then it's equal to 1, so it's equal to its maximum, okay? So since it's equal to its maximum for some interior point in the disk, then the maximum principle says that it has to be constant. Okay? Which implies that g of z is equal to lambda. And absolute value of lambda is equal to 1. Okay, so maximum principle implies that g of z is equal to lambda. But absolute value of g of z for some point, okay, is equal to 1. So absolute value of lambda is 1. We have no choice. So this is maximum principle. Okay. So if equality occurs, occurs for some point, right? So let me write maybe g of z0 here. For some interior point z0, this is b. But for some z0 in d. Okay. And it implies that it's constant everywhere by maximum principle. Questions? Is it clear? Okay, so now the question becomes, how can I use this? Okay, so the first thing I can show you is this. You can answer the following question, or try to address this following question. So application. To what extent are conformal maps unique? Okay, so what do we mean by this? So for instance, suppose that f and g are both maps from some omega to some d, okay? And yeah. What I want to say is, okay, so let's say that omega contains 0. Let's say it's some other domain, okay? So let me just do this for simplicity. So assume omega contains 0. But it's just for simplicity, okay? If it does not contain 0, then you just have to elaborate with Möbius transformations so that things go the way we want, right? So let's not do that now, but you understand that you can do this. So then you can look at F composed with G inverse. So what does F composed with G inverse do? It goes from D, takes G inverse, goes to omega, then it goes from omega back to D. Okay? So it's a map from D to G. And it takes 0 to 0 in particular. Of course, you can put weaker hypotheses so that I can still apply and say something like this. But let's just consider this case as an application, as an example. So let's assume this. And now by Schwartz lemma, what do we get? So now, I mean, the point in doing this is that now we have a map from a unit disk to a unit disk, and we can apply Schwartz lemma to F composed with G inverse, because it goes from 0 to 0. And what does Schwartz lemma say? So it says that absolute value of F of G inverse of Z, this function, is less than or equal to absolute value of Z. Okay? And it says something about the derivative. Okay? But in particular it says this. So it says this. Now,
Condition.
sorry?
It's condition.
No, this is not the condition. This is a conclusion. This was 1. 1, 2, and 3 were conclusions, not hypotheses. The hypothesis to apply Schwartz lemma is that you have a map from the unit disk to the unit disk that sends 0 to 0.
Yeah.
And then this was the conclusion. No?
And the Schwartz lemma, that was the condition, and we get this conclusion. That f of z is the rotation.
No. So Schwartz lemma was, if you have a map from a unit disk to unit disk, satisfying this, then the absolute value of this map in the point z is less than or equal to the absolute value in z. And the absolute value of the derivative in 0 is less than or equal to 1. And if we have equality, then this holds. So it's okay, so we get this. That the absolute value of this is less than or equal to z. Okay. But now if we set w to be equal to f of g inverse of z, what do we get? So we define it like this. So then f of g inverse of f of w. So then then let's write it. So then we can look at this. G of f inverse of z, of w, sorry. Now I interchange w and z compared to my notes, so I will be completely confused if I try to read this, but yeah, so I'm sorry. So then I look at g of f inverse of w. Okay, so going back in the other direction. Okay, so then this is equal to, so w is equal to this.
G is 1 to 1. It's considered to be 1 to 1.
So I mean, there are no assumptions except this.
But how we compose with G minus?
That it will be.
Yes, minus 1.
No, so they are invertible, but so for sure there is some good reason for that. I mean, we have discussed a lot about when holomorphic maps are invertible or not, but
the derivative is not 0 probably.
yeah, right now it escapes me, but I will think of it. Yeah, what you can do. So you look at this thing, and this is of course equal to the absolute value of W. Okay, because this is the inverse of that. So this is equal to the absolute value of W. No, sorry, it's sorry, yeah. Okay, so this is, am I confusing? No, yeah, this is equal to W, and this is greater than or equal to, oh, making such a mess. So I want to use this and put it inside here. That's what I want to do. So from this I get Z is equal to, so I get that, yeah, okay. It's greater than or equal to the value W. Please check that I did not confuse the letters. And on the other hand, so by Schwartz lemma, again, we get that, but now applied to this this function, g of f minus 1, we get that g of f minus 1 of W is less than or equal to absolute value of W. Did I get this right? I'm pretty sure I got this right, but you follow? Okay, good. So g of f inverse of W is less than or equal to W, and it's greater than or equal to W. So we have equality. So we have this thing is equal to this thing. Okay, and this implies that g of f inverse of wz, whatever we call the variable, is equal to lambda z, where absolute value of lambda is equal to 1. So lambda is a constant, absolute value 1. Okay, and this means that g of z is equal to e to the I theta f of z for some theta in 0 to 2 pi. So what it says is that if you have two maps from any domain, now just assume it contains 0. So any two maps that maps 0 to 0. So you have this omega is this, and 0 is inside. So if you have any map from this to the unit disk, any two such maps that map 0 to 0, they differ just by a rotation. So essentially these kind of maps, they are almost unique in a certain sense, up to this constant lambda with absolute value 1. Which is quite remarkable, no? Because a priori you could imagine all sorts of maps that map this to this. But the fact that we're looking just at analytic maps, this shows how this is yet another of many things, many features of analytic maps we have seen, that they are so special that we are essentially unique if we want them to do this. So this is pretty remarkable. So they are essentially unique. Another important thing, now a nice topic, is automorphisms of the unit disk. So I don't know how much contact you have had before in your mathematical lives with the topic of automorphisms, and in what context you have seen it. Sorry?
6 times.
6 times you've seen it. Oh, that's a very precise answer. What? You mean in 6 courses? Or?
Yes, I mean, 6 different, but maybe I forgot.
6 and 4 got 6 and 4 got.
Okay, but so automorphisms, so what does it mean? So this you know, but let me write it anyway. So okay, let U be in C be open subsets. Then we say that first of all a holomorphic map okay, so what am I doing here? So let's just say, what is an automorphism? Someone can tell me. What does an automorphism mean to you, this word?
In general.
Just,
yeah.
no, just in general.
Okay, so it's transformation that preserves the self-structure of the. So we have set and we have structure on it, so it's map that preserves the structure of the set itself.
Yeah. Basically, it's an isomorphism from the set to itself.
Exactly.
Right?
Yeah.
It's an isomorphism from the set to itself. And what is an isomorphism? Well, it's a bijective morphism.
Yeah.
But what is a morphism? And this is the important thing. So morphism is something that is a map that preserves the structure. So a group morphism is something that preserves the group structure, but you have all sorts of morphisms, depending on what kinds of objects you study. So in differential geometry, a morphism might be a C-infinity map, because you want to preserve a C-infinity structure, okay? It's an infinitely differentiable map. Or, you have a ring morphism, you have all these things, right? But in complex analysis, what do we want to preserve? Well, we want to preserve a complex structure in whatever sense, whatever that means. And preserving the complex structure, that is done precisely by holomorphic maps, which are our morphisms, okay? Holomorphic is morphism in the category of complex analysis or complex geometry. And being a bijective holomorphic map is then what we want to mean by isomorphism. Okay, so holomorphic map, which is bijective, is called a biholomorphism. Or biholomorphic map. Okay, and biholomorphic map from U to V. Biholomorphic map, F, U to V. Which is bijective is called a biholomorphic map from U to V. And now if U is equal to V, we say that it's an automorphism. Okay? An automorphism on U or on B, whichever letter you want to keep using. They are the same set. Okay? So a biholomorphic map from a set to itself is an automorphism in the category of complex geometry. And you write like this: aut of U to be the set of automorphisms on U. And this is a group, by the way, so group with composition. As the group law. Okay? So we have the automorphism group. And now we want to study the automorphism group. So, studying automorphisms is extremely important because, why is it important? It says something about the structure of our geometric objects that we want to study. So now we're studying the unit disk. Okay, so you'd think that we understand the unit disk pretty well. We can picture it. But in general, you have a 17-dimensional manifold that is supposed to represent something, or the 6 real dimensional, 3 complex dimensional manifold that's supposed to represent part of our universe. This calabial. How can we understand what it looks like? So at least we can look at the automorphisms. So are there many maps that preserve the structure that we're interested in? In that case, it's likely that the object is in some sense fairly symmetric. It's a fairly nice object, but if you have a very weird object, then if you have a circle, it's very nice and symmetric. So you would expect that you have many automorphisms. Like you can, first of all, just rotate and it preserves every structure, or you can, there are things you can do. But if you have something which is very horrible and very asymmetric, you would expect maybe not to have many automorphisms at all. So if you compute these groups, which you can do algebraically, you can get information, quite a lot of information in fact, about your geometric objects, even though you cannot picture them. I mean, as far as I know, no human can very well try to picture a 6-dimensional manifold that is completely abstract and, what is going on. So at least we can compute these algebraic invariants. This has been the approach of mathematicians. So understanding the automorphism group is great. And understanding the automorphism group of a disk is extremely useful because the disk is related to, so if you look at compact complex manifolds of dimension 1, then there are only 3 types, and the most common type is strongly related to, is the one with negative curvature, which is strongly related to the unit disk. In fact, it is covered by the unit disk. And so if you can understand the automorphisms of the unit disk, you understand most of the compact complex manifolds of dimension 1. Okay. Not part of the course, this was just some bonus motivation. Now, so question, what is this group? Automorphisms of a unit disk. And how can we understand it? So first, we have the following lemma. That, the only really obvious thing is that the rotations are automorphisms. Okay? So it is clear that this is, it is clear that it's a group actually you can check. So you can check that it's not empty. This is trivial. And that if you have several automorphisms, then their composition is still an automorphism. But apart from the rotations, we have other maps that are automorphisms. And you can write down, in particular, Möbius transformations that are automorphisms. So a family of Möbius transformations. So for every A pointing D, then you have this map phi A of Z, defined by A minus Z over 1 minus A bar Z. So here, note that A is in D, so absolute value of A is less than 1, but it's a complex number. So then these are automorphisms of D. So this is the lemma. Okay? And then let me write down, before I prove this, let's write down the theorem that, in fact, all automorphisms of D are of the form f of z equal to e to the I theta phi a of z for some theta between 0 and 2 pi. So in fact, up to an additional rotation, these are all the automorphisms of the unit disk. So the automorphism group consists of all such elements. Phi A, this Möbius transformation, that's this. And this is a great exercise to show all these things. First of all, why are these automorphisms of the unit disk? Then you have to show that this Möbius transformation maps the disk into the disk. You have to show that it's bijective. And to show that it's bijective, you would use Schwarz Lemma, for example. And for sure, whenever you see something like this, like show that all the automorphisms are of this form, then you just know that there's going to be a Schwarz Lemma inverse somewhere, because you see that you work on something that goes from the disk to the disk, or even if it was from the upper half plane to the upper half plane, you remember you could take it to the disk and translate the result. And then you essentially want to show uniqueness of something, right? You want to say that if you compose f with the inverse of this, or divide by this with an appropriate map, then this map is constant. It's constant. So you just know that Schwarz Lemma will be in there. So let's see. How much time do I have, and what do I want to do? Do I want to start with the lemma? Do I want to start with the theorem? I think I will actually just go on with the lemma. So proof of lemma. Because to be honest, I think it's very instructive, because this seems like it might be extremely simple, but how do you show the fact that it's bijective, for example? You know? So let's just see how you can do it. So we have to show it's an automorphism. So we have to check several things. So I start listing the points that we have to check. So first of all, we have to say that actually this is a holomorphic map, right? So Mabi's transformation is not holomorphic in general, because okay, it's a fractional thing, it's a rational map, so we have to see that this is not 0. So this is the first thing to check, right? So phi A is defined and holomorphic. Okay, so D, let's put it like that. So of course, this is true, let me write it in color, in orange, so this is true for any z, except when this is equal to 0, which would happen when z is 1 over a bar, a conjugate. But the absolute value of 1 over a bar is 1 over absolute value of a bar, and this is less than 1.
It's not on disk.
Sorry? So this whole thing is greater than 1. So this is greater than 1, so it's not in the disk. So not in D. Yeah. But still we should not forget this, that we have to actually check that everything was correct so that it's holomorphic. So phi A is holomorphic in D. Second point is to show that it takes the disk to the disk. Okay? This is the second point. So how can we see this? So anyone has an idea, by the way?
You can take Z in the boundary on the disk and show that its image is also the boundary, which is true because this one is exactly Z times Z bar. We put Z and then the thing will cancel and we get 1. So the image of the boundary of the disk is exactly.
Exactly. So we check that the boundary goes to the boundary, and then so you can use this actually that we used last time. I mean, many lectures ago. We said that we show boundary goes to boundary, so then the inside of the disk goes to either the inside or the outside of the disk, because it cuts the Riemann sphere in 2 parts, right? And the map is continuous. You remember this? So then we just have to check 1 point. So actually, yeah, we do whatever you were taught. It's a lack of time. So this one we do in the usual way. This one is checked. Okay? Now, next part, the interesting part is phi A is bijective. Okay? How do you do this? So to see that it's bijective, okay, now there is a sort of funny way of doing this. So let me show you this funny way simply. I mean, this is maybe not completely natural. Yeah, I think you have to try a little bit before you come up with this solution. But let me still show it to you so that you will have seen it. So phi A of A is equal to 0. Note this. And note that phi A of 0 is equal to A. So A goes to 0 goes to A. So this is a special feature that is worth remembering actually about this map. So this implies that if I take phi A twice, and then it sends 0 to 0, and it sends A to A. Okay? So it takes A to 0 and then back. Sorry? And now you can apply Schwarz-Lemma. But to notice this, I mean, I don't expect that everybody just goes, of course, you probably will notice this, and then You have to look at it maybe for a few minutes before you see this. But now you can, anyway, now we have noticed this. So now we can apply Schwartz lemma. So how do we apply Schwartz lemma? What is it that we can observe immediately, in fact? So because of this, we can apply Schwartz lemma. And then we also have this. So if I want, I can put in particular absolute value here, right? So this one was just to apply it, but just the fact that the absolute value of this is equal to this doesn't say anything, because as was pointed out, it has to hold this equality for a non-zero point. So by Schwartz lemma, oh shit, color. So by Schwartz lemma, it follows from this for a non-zero A, okay, because A is, okay, of course A is not zero. If A is zero, then whatever. So by Schwartz lemma, so, okay, for some A non-zero, let me just write this, implies that phi A of z is equal to lambda z for some constant with absolute value 1. So it's just lambda times the identity map, right? Okay. So now, so we have shown that up to a rotation, up to this lambda, phi A composed with itself is the identity. Okay, but so what we're going to do actually to show it is bijective is find its inverse. And I claim that phi A is its own inverse. Because actually now we go back to what we had. So not only did we have this in absolute value, right? But we had an exact equality. So if we have it in absolute value, then you can understand that you need to take this rotation into account. But now phi A of A is equal to A means that it's also equal to lambda times A, right? So it means that lambda is in fact just the real number 1. Okay? So it means that it's a real number 1, and hence phi A is the identity map. Okay, and this means that phi A is equal to phi A inverse, and in particular, phi A is bijective. And this means all of these things show that phi A is an automorphism. So it's an element of the automorphism group. Okay, and that I think is all I have time to say today. Next time we can show that these are the only automorphisms, again using Schwartz lemma. You can try to think of it for yourselves. Okay, and then next time is the last lecture. So then we will finish off with some nice things. Okay, and the next time is going to be, so you have some, so it's tomorrow, it's an exception, right? So, because Friday is All Saints Day, so nobody is coming to ICTP on Friday. So tomorrow you have the special event until 4 o'clock at Adriatico, and so I will be here, let's say at 4:30. So this is what I agreed with Patricia. So if you come after the special event tomorrow, and then the lecture is scheduled at 4:30. Okay, tomorrow. Okay, thank you.